Okay. Hello, what's up guys? Today I'm going to talk about the definition. Okay, first of all, I would like to introduce our group members. Okay, we've done introducing our group members. So we are going to talk about our topic, which is the first order differential equation.
What is first order differential equation?
So to answer your question, the first order differential equation is an equation that involves an unknown function and its first derivative, but no higher order derivative. So the application of solving problem using differential equation is Brachistochrone problem. So, a Brachistochrone problem, which translates to shortest time, is a problem that uses curve and minimize the time taken for an object to slide under the influence of gravity between two given points. The goal of this problem is to identify which path can minimize time taken of moving object from point A to point B. The solution to this problem is a cycloid, a curve traced by a point on the circumference of a circle rolling along a line. So, hey, who are you? Why are you disturbing me? Sorry.
By sheer coincidence.
Hola chicos, lo que están hoy les traigo un experimento. Se puede ver que esta le digamos a todos. Claro que voy a poner en cámara lenta para que puedan observar ustedes de mejor manera.
What do you guys understand about this video?
I don't understand. Why the curve is faster?
I don't really understand about this topic too. How about check?
I think I know someone that can help us to explain this video. Let me call Amin and Ryan to help us more about this video.
A lot of boring math later.
Hey guys, Amin and Ryan already made us this video.
Oh, let's take a look.
Hey guys, so this is actually a pretty ancient problem in mathematical physics. We want to roll a ball down from point A to point B. We want to find the path of fastest descent. Let's try three possible situations. This straight path, this purple curve, and this yellow arc. Let's see what happens. Unsurprisingly, yellow wins. But let's ask a deeper question. Among all the infinite possibilities that this ball can go down, which is the curve of fastest descent? Which is the Brachistochrone curve? Greek for shortest time. Seems like quite a hard problem. We need to consider the incline, the velocity, the weight of the ball, normal forces, maybe even do a little rigid mechanics. But luckily for us, we don't need to do any of these things. What we need to do is turn our thinking around. The question isn't what's the curve, it's where have we seen this before? If we look around, we'll find something that always takes the fastest path between any 2 points. In fact, we don't really need to look at all. That thing is light. Let's see what we mean by this exactly. Consider a glass of water, and let's trace the path taken by a light ray as it goes from point A to point B. Rather than going to B directly, the light is going to travel with velocity v1 in the less dense medium, then entering the denser medium, change its velocity to v2 and its direction from alpha 1 to alpha 2. Now we know from basic optics that the sine of alpha 1 divided by v1 is equal to the sine of alpha 2 divided by v2. This is known as Snell's law of refraction. And the reason that light bends like this is because this actually is the fastest path between A and B. But this doesn't look like much of a curve. That's because as long as light is traveling in one medium, it's just going to take a straight path since it has a constant speed. So how do we vary the speed of light? Well, that's very simple. We vary the density of the medium and trace the path taken by the light each time. As the medium approaches continuously varying density, the path taken by the light approaches a smooth curve. If we take the tangent at any point along this curve, measure the angle and the velocity, then we know that it must obey Snell's law, that the sine of alpha over v is a constant. Since this is the fastest path between A and B, this is a fundamental property of the Brachistochrone curve. So let's return now to our original problem. We're going to draw our curve from A to B, and just assume that this is the curve of fastest descent. Our goal is to find a mathematical expression for the height, which is the equation of the curve. Assuming that this curve is the Brachistochrone is the same as assuming that it obeys Snell's law at any point. Once again, sine of alpha over v is a constant. Now, how do we find the velocity? We can use the conservation of energy. As the ball descends, it loses potential energy and gains equal kinetic energy. Half mv squared is equal to mgy. So v is equal to root 2gy. That's our velocity. As for the sine of our angle, it's actually much easier to deal with this complementary angle, beta, where beta is equal to 90 minus alpha. We know that sine of alpha is equal to cosine of beta, and applying a little trigonometry is going to get us to this expression here. What is tangent of beta here? Well, that's the change in y over the change in x, which is the derivative of y with respect to x. We have our sine of alpha. Combining everything together gives us this hairy-looking equation. But we know that the right-hand side is a constant here. So we can just remove our g and get rid of this 2, and no matter what we do to the left-hand side, that right-hand side is still a constant. In fact, this is how we obtain our differential equation for y. This is the equation of the Brachistochrone curve. If we rewrite this equation with Leibniz notation, we see that it's separable in dy and dx, which means that we can just solve it straight away by integrating both sides. Unfortunately, the result is a bit hairy, and it doesn't really tell us much about the shape of the curve, which is what we really care about. If we go back to the original equation and express this part under the square root as the tan of a new parameter phi, then by implicitly differentiating, we get an expression for dy that we can then integrate in terms of phi to get y equals c sine squared of phi plus an integration constant. Getting rid of the sine squared using a trig formula gives us this neat expression for y. Doing the same thing for x, we can start with dx equal tan phi dy, and we can expand this dy based on what we just got from the implicit differentiation. Multiplying, we get dx equal 2c sine squared of phi d phi, and again, getting rid of the sine squared by the trig formula gives us an expression for dx that we can integrate to get x equals c over 2 phi minus sine 2 phi plus an integration constant. To find these constants, we apply our boundary condition that we start at the origin. The constants vanish. If we now make an aesthetic choice to let a equal c over 2 and theta equal 2 phi, then we're left with these two equations. These are the parametric equations of the Brachistochrone curve, and they may be familiar to you, for they are the standard parametric equations of a cycloid. A cycloid is the path traced by a point on the circumference of the circle as it travels down a path. A is the radius of the circle, and theta is the angle as the circle rolls around. You can see that the circle traces the path of the Brachistochrone curve as it rolls. That's the solution.
Do you guys understand?
I understand it now.
Fahim Tom, fahim nggak?
You guys then consider like and subscribe.